All right. Am I recording? I'm recording, yeah. Let's see here. Okay, sure. All right, so I'm sharing the screen again, and wanted to mention the something I mentioned on the website that might be useful as you're learning about NMR. Is this tool called Nmrdb that basically what it does is we're used to going from NMR spectrum to structure, right? What if you have a structure and you want to make an NMR of it, right? This Nmrdb is a tool that allows you to do that, and it's kind of useful. You can draw a simple molecule and see what the NMR might look like. So it's a useful educational tool. And if you're in the lab course, you're probably going to be doing this a lot, because in the lab course you're making molecules, and then you're maybe simulate the NMR, and then you can see, oh, does it match the real data? Can you show how it works? Yeah, sure, why not? I'll do a quickie. Can you show how it works? Yeah, I'll click here. Predict Proton Nmr. So you go in, and then usually you either do predict Proton Nmr or predict carbon NMR. Do predict Proton NMR, and then it actually starts with a structure like propyl benzene, a nice simple molecule, right, with five CHs on the aromatic, and a CH2 and a CH2 and a CH3. So you can actually see it. It already shows you the structure of that, the predicted NMR spectrum of it. And I think you can use the mouse to sort of zoom over it. And, like you can see the triplet. You have the CH2 next to the benzene. This would be like a hextet or sextet, six peaks split. It's the CH2 in the middle. It's nice you can move the mouse, so I think it lets you do that. I think, I think, okay, if you zoom in too far, I think you can double click to get out. Yep, I double click to get out. Let me just zoom in here real quick. If I move the mouse, if I move the mouse over the peak, it tells you where the I used to actually show it on the chemical structure. Maybe there's a way to do that. But that's clearly the middle CH2, because it's a sextet, right? 6 peaks, 1, 2, 3, 4, 5, 6. And then on the end we have the methyl is the triplet of 3 protons, right, etc. And so you can draw your own chemical structures and actually simulate them. Let me try to do that real quick. I'm just going to draw, like, let's see. Oh, sorry, clear. What's this question mark thing? Let me try a different browser. Yeah, I'm trying Chrome now. Blah blah blah. I agree. Yeah, there we go. It's a little better. I think there's less stuff on the screen. Let me try this to draw. There it is. I use the line. So I'm going to draw maybe there we go, with the bromine or chlorine out here or something like that. So I just drew some random structure and I hit simulate spectrum. Okay, so now it simulated the NMR spectrum, and you expect 3 CH3s as a singlet because there's no neighboring protons. That's out here at 1. And then you have the 2 CH2s. The downfield one is probably the one next to the chlorine, right? They're both triplets. So you can kind of zoom in and see this. It's nice that we can draw structures and get like a predicted spectrum. Oh, actually, and here's a nice thing. If I move the mouse over like the left CH2, you see how it highlights it? You're like, oh, that's the CH2 with the chlorine on it. Let's move the mouse over here. Oh, it's the other CH2. What about this singlet? Oh, it's the 3 methyl groups, right? So it's a pretty cool utility, and it's free, totally free. All right. Just while we're showing cool stuff, I actually, for the last 6 weeks, have been synthesizing a molecule. I'll show you it actually, one second. So I'm actually a chemist that does synthesis in the lab, and I'll just, without going in detail, I'll just show you what the synthesis was. So I did this full synthesis. It's a whole series of organic reactions to build a complicated molecule that is at the bottom here, which is an inhibitor of a protein that I'm interested in. And a lot of these reactions you can actually understand by the end of this course. But yeah, it's a pretty complicated multi-step process. And I made this, and I actually got an NMR of it today in the laboratory, because I needed to prove this for my project, that prove the chemical structure. So let me, I actually have another simulator that I use, which is cost me about $1,000 back before simulators were free. So I was able to first draw the structure and simulate the spectrum, the proton and carbon NMR spectrum. So I'll just show you that real quick. So this is like a predicted proton NMR of that structure. So and I'm able to move the mouse over all the peaks and see, where I expect all these signals to be on the structure. Okay, and then I actually took the real NMR, and it, for the most part, matched this identically. So I'll show the real NMR structure. Well, this is the carbon. So this is the real proton NMR of that molecule, and everything matches. I'm able to assign all the letters of the chemical structure and where they reside on the real NMR. So this is like a real research project, and we also have a couple impurities, the little X groups, which I know what they are also. But anyway, this is cool. It's a real example of proton NMR to characterize a real molecule after 10 steps of synthesis. I did 10 reactions in a row, and then I isolated this pretty clean. Here's the carbon NMR, same thing. I drew letters for all of the carbons in the molecule, and I was able to assign every one of those as well, kind of using the simulator to help me a little bit. But that's pretty cool. It's a real research project, and this is the best inhibitor of a protein I work with in the world right now. You cannot buy it. You cannot purchase this. So I had to make it myself, and I finished it. Yay! Nice accomplishment. All right, so let's get back to our stuff. I wanted to on this. So on the syllabus, just wanted to remind us where we are. Kind of, we're a tiny bit behind, but this is normal in this course. We're on this Thursday, and we're going to start the Alkyne chapter in a little bit, and eventually exam 1 will only be over chapter 10 and chapter 13. Okay, so and normally exam 1's a little earlier, but it's just we're going to do it in the face-to-face period of the class. I'm going to try to post all the exam 1, like sample exam and all that stuff, next weekend, next Friday probably, and then you can start getting ready for it. If you can do really well on exam 1, that's a good setup for doing well in the rest of the course. All right, and then remember, annoyingly, exam 2 is kind of quick after that. It's 2 weeks away. And then we got this huge break till exam 3. So we're going to struggle a little bit early, and then we get a nice big break, and then we'll be done with the course before you know it. All right. Okay, and then another thing on the syllabus, this is really, really important, this proton correlation chart. You should really maybe tattoo it on your hand or something to really remember these key regions, especially as we're doing these problems that we're doing. Like the aliphatic region is kind of the upfield region, kind of CH3, CH2, sort of boring ones. 2 to 3 is next to pi bond. Remember that, 2 to 3 next to pi bond. 3 to 4 is next to electronegative, so it's like an oxygen or a chlorine or something. 4 to 6 is kind of alkene, and you're less likely to see alkenes, but we will. The exam is not open note. No, exam is not open note. It's a normal in-class exam, but I give you a lot of preparation material. This will be on the exam though. You will always have these little charts. Benzene region, kind of 6 to 9-ish. Aldehydes, 9 to 10. Carboxylic acids, 10 to 12. All right, cool. So let's get back to what we were doing then. Elucidation problems. Remember these things? So we already did a couple of these, and I'm going to do them on my webcam again. But like, remember problem 1? We made a little table. We made a little table of the signals. Eventually, we realized, oh, we're missing a carbon and an oxygen. Remember that? And then we said, oh, we must have a ketone, right? And then we put it all together. So that's kind of the strategy: is start with UN, the degrees of unsaturation. Make a little table. Each row of the table becomes a substructure, a piece of the puzzle. And then if there's any mystery functional groups, like we had a ketone here, then you have to draw those too. All right, so let's get back to my other webcam and we'll continue here. Whoopsie. So 1 second. Sorry. Stop share. So, and I'm not going to review this problem, but the first one in detail. The first problem, remember, once we made our little table, we figured out our pieces. Then we eventually saw, oh, we have a ketone. And then the pieces snap together, and you can only get this kind of ketone product. So let's go to problem 3. We haven't done problem 3 yet, so let's try problem 3. Okay, what's our first step? What's the first step? UN. So you should be all experts at UN by now, I hope. Ignore the oxygens. It's 2 times 9. We'll just do the plus 2 before, minus 10. All over 2 is 18, 19, 20. 20 minus 10 is 10 divided by 2. 10 divided by 2 is 5. The fact that there's 4 probably, there's 4 plus 1. 4 suggests maybe a benzene. And what's the thing that usually comes around the 7 to 8 region? Maybe benzene, right? So that's a good indicator that we have a benzene. We also have a quartet and a triplet. Anybody remember what a, I mean, that's a kind of a dead giveaway. A quartet and a triplet is a dead giveaway of an ethyl group. So that's probably going to be an ethyl group, a CH2, CH3. And also this is around 4, so that's going to mean something. The quartet around 4, So let's make our little table. Delta H S. Whoops. Delta H and S. Okay, well, I always want to be able to see it all. Let's try that again. Delta H and S. All right, we have delta H and S. Delta is the chemical shift, and we'll just go left to right, 7 to 8-ish. It's kind of this whole mess of 5 protons. I'm just going to assign that as a single thing. I'm just going to say 7 to 8, and you can often do that in the aromatic region. Just say 7 to 8. It's 5 protons, And it's kind of a mess. And that's common in the aromatic, especially if you have 5 protons. So what do I write? When that happens, I usually write malt. Okay, the rest is actually pretty straightforward. Now we have, was this about 4.2 and 1.2. Okay, 4.2 and 1.2. 4.2 and like 1.2. The number of H's for 4.2 is 2 protons. And the splitting of it is a what? A quartet, right? And we say Q. And then 1.2, the number of protons is 3. And the splitting is a triplet, or T. Okay, now we draw, what's the next step of our procedure? We make a table. Then we try to convert each row of the table into a piece, like 5 protons in the benzene region, aromatic region, right? Is in 5, remember the 6 protons total on the benzene. So if it's 5, we saw this last time, if it's 5, how many are left over? 1, right? So we say we call it a monosubstituted benzene. I'm just going to draw a little squiggly benzene. A squiggly with a benzene. That's what this thing is, right? 7 to 8 is a squiggly with the benzene. What is 4.2? Anybody know? 4.2 is how many protons? Is it? Yep. I see. Somebody said it correctly. CH2. You're really looking at the H column here. It's like, oh yeah, you have a CH2. How do I draw a CH2 substructure? I say squiggly CH2 squiggly. Squiggly CH2 squiggly, right? What about this? A 3 is probably a CH3. And I draw how many squigglies on my CH3? There's 1. CH3, okay? Cool. All right, so we got some pieces, right? All right, do we have all the pieces? Let's count them up. 6 carbons, 7, 8 carbons. Did 8? Uh-oh, there's 9 here. That's a problem. H's, we got 5, 6, 7, 8, 9, 10. Got the 10 hydrogens. But we're missing 2 oxygens also. So, and we also have, UN is 5, which is basically equal to 4 plus 1, right? Because we have 4 in the benzene. Remember, a benzene is 4 plus 1. Okay, so this is where we have to figure out our mystery functional group. Okay, remember how before we had a C and an O, and we said, oh, it's a ketone, right? Here we have a C and 2 O's. So what are my options? Tell me my options. C and 2 O's and 1 UN. There's 2 options, basically. Almost. There's only 1 real option, but we'll pretend there's a second option. A carbon with 2 oxygens. Functional groups. What are your functional groups? You know, ketones. You know, aldehydes. So it's not a ketone because that's only 1 oxygen. Carboxylic acid. Okay, cool. I see. I hear carboxylic acid, which is wrong, but it's close. Carboxylic acid is 1 option. The problem with that is it's a carbon with 2 oxygens, but it also has an extra proton, right? So carboxylic acid's out because it has an extra proton. We already have our protons. We have 10 protons. If you had this, it would be proton number 11, and there's no 11, right? So it's not this. I see aldehyde. Why is it not an aldehyde? Why is it, this is an aldehyde. Aldehyde. Why is it not an aldehyde? Because an aldehyde would also have a proton and only 1 oxygen, right? Okay, so let's see. I see somebody got it. Somebody said ether. Let's just go through these options. Not an aldehyde, not an ether, because it doesn't account for the 2 carbons. But somebody said it correctly. Ester. It has to be an ester. It has to be an ester. And yeah, a carbon and 2 oxygens, because we're missing a carbon and 2 oxygens. The correct functional group is going to be an ester. All right, so I'm going to draw that. kind of up here. So it's an ester. This is sometimes the most challenging thing, is figuring out what your mystery functional group is, right? An ester, and you also just have to know your functional groups, right? It's good you came up with a couple. We had a couple bad ones. Eventually got to the good one. A carbon with 2 oxygens and no more protons, right? And it's totally an ester. Ester, right? Okay, cool. All right, so now now we have the pieces, right? How do we snap them together? Is there any of this information that really stands out that helps us connect this all together? I see a bunch of information. I see, yeah, CH2, CH3. Somebody in the chat said CH2, CH3. Yes, absolutely, the CH2 and the CH3 are connected, right? We know that because the CH3 is a triplet. That means it's next to 2. And the CH2 is a quartet, meaning it's next to 3. So we can erase those things and draw CH2, CH3. And then I get my eraser out, and I erase these because they're gone now. We just massively simplified the problem. Now we have a middle piece and 2 end pieces. The only question is how to connect them, because this middle piece is different than a ketone. Remember, a ketone has 2 equal sides. This does not have 2 equal sides. It's like, oh, we have the oxygen side and the C double bond O side, right? So what piece of information tells us like where the oxygen is connected? And somebody said it correctly. OCH2CH3, OCO, CH2CH3. And the reason is because the oxygen is downfield, or the CH2 is downfield, right? The CH2 is at 4.2, that's very downfield. So that totally tells us, oh, that CH2 has to be connected to the oxygen. So then we just get the eraser out and draw CH2, CH3. And we can erase the ethyl group. And now we see, well, there's only one way to connect these. It's going to be a benzene, C double bond O, O, CH2, CH3. The final answer is that. That's the ester, right? It's an ethyl ester of benzoic acid. So there's our cool process again. It works every time. Can you explain what you meant by 4 plus 1 and what those numbers came from? Yeah. Okay, so when I said 4 plus 1, that was over here. But remember when we calculated 5, okay, if it's above 4, well, say it's 4. Say your UN is 4. UN of 4 is almost always just a benzene. If UN is 4, it's a benzene. So 5 would probably mean benzene plus something else, right? That's exactly it, because UN is, of course, the number of double bonds in rings. Number of double bonds in rings. So a benzene, of course, has 4. The ring is 1, and you have 3 double bonds, right? That's 1, 2, 3, 4, right? So when I see 5, it always to me means, oh, you must have a benzene plus something else. And then we're like, what is it? With a lot of head scratching, head scratch, head scratch, head scratch, we eventually said, oh, it must be an ester. And that's because we were missing a carbon and 2 oxygens. Okay. So 5 is almost always going to be a benzene plus like a ketone or ester or something. 4 would just be a benzene, right? If you see 4, you're almost always going to think just a benzene. All right. Cool. All right. Let's do another one. We did this one last time. I'm not going to do it again. Of course, this was a case that this is problem number 4 of the PowerPoint. Problem 4. UN was 0, so no double bonds, and you know it was a pretty simple 4-carbon alcohol. It was just isobutyl alcohol. Remember isobutyl? That's an isobutyl. Isobutyl. Functional group from chapter 2 when you learned about branched substituents. Isobutyl alcohol. Okay, let's try number 5. Okay, so we got, let's try this one. Okay, so there's the spectrum. I'm gonna go up to the molecular formula. Start there. Oh, we see something that disappears with D2O, maybe an OH, right? Okay, so UN is, again, we ignore the oxygens. It's, do the math, it's 1. You should all be able to get 1 for that. So no benzenes, definitely no benzenes, but maybe a double bond O or something, right? So let's do our little, almost always, UN1 is just a double bond O. Okay. Table. Delta H S. A delta, well, we got something at 12. How many protons at 12? 1. Splitting, singlet. Then we got 2.1, triplet. 2.1 triplet of 2 H's. Then we got, oh no, this scary mess. Scary mess at 1.7 of 4 protons. How do we represent a scary mess? We say it's a mult. But at 1.0, we have 3A, right? Whoa. At 1.0, let me fix my camera a bit. At 1.0, we have 3 protons, and it is a triplet. Okay, 1.0, 1.0, 3 protons, and it's a triplet. Okay, there's our table. That's a good start. We got our UN, we got our table. What do we do next? Let's build this going upward. I'm going to go from the bottom up. So what's this 1.0? 3 protons. It must be a. You're focusing on H at this point, and it's a CH3, right? What's 4 though? Is it a CH4? No, it's not a CH4. It's a, and somebody said it correctly. It's probably going to be 2 CH2s that happen to be overlapped because they're in the same ballpark. So 2 CH2s. CH2, CH2. So you have a CH3, CH2, CH2. What's this one? 2.1 is also 2. There's a triplet. Let's say CH2. Okay. Now, this one, it really helps us if we can remember our chart. Remember the chart? And there's only one thing that comes way downfield. Way downfield. Well, somebody says OH, and that's correct. You know it's an OH because it disappears with D2O, right? But then if we also go look at the chart and we look at the 10 to 12 region, because 9 to 10 is usually aldehyde, 10 to 12 is carboxylic acid. Somebody said it, yeah, carboxylic acid. So right now for you guys, only one thing comes around 10 to 12, and that's a carboxylic acid. So how do we draw a carboxylic acid substructure? It's that, right? Carboxylic acid. It's a squiggly C double bond O OH. With that, and we also, what was our UN again? UN was 1. Oh, well, there's that. No mystery here, right? Usually, right about now, we have to scratch our head until we figure out which mystery functional group we got. But we didn't have to do any head scratching here because of the 12. The 12 really gave it away. Now, this is an insanely easy problem because you got how many N pieces? What's an N piece? An N piece is 1 squiggly, right? You have a CH3 on one end and a carboxylic acid on the other end, and 3 CH2s in the middle. So you've got a big long carboxylic acid with how many carbons? 1, 2, 3, 4, 5. 5 carbon carboxylic acid. So the answer is 1, 2, 3, 4, 5. It's just pentoic acid. Pentoic acid. Now, what if we didn't make those connections? Well, we might say, you know, that CH3 is a triplet, so it must be connected to other CH2s. There's a bunch of CH2s, right? Now, like that CH2 is a triplet, so it's connected to CH2s. All of that kind of is consistent with a big long chain. Triplet, triplet. You know, it's like we have the one at the end is a triplet, that one's a triplet. So usually, you know, in this case, we just kind of put it together. And these two CH2s are multiplet, and that's because there's not really much next to them to differentiate them. So they are both kind of a crazy mess. And that happens, that you get overlap sometimes. And that's what we got. Cool problem. Easy. Too easy. All right. Problem 5. 6 now. Was that 5? 5 is done now. Let's try 6. Any questions? 12 really saved us, though, right? If you're a master at the chemical shift chart, you can sometimes get some really good information. Okay. Okay, problem 6 is so easy that I am going to I'm going to expedite this one a little bit. Problem 6, there's not very much stuff, right? It's C9H12. What's UN? UN is, I think it's 4. 2 times 9 is 18. 20 minus 12 is 8. Divided by 2 is 4. Yeah. So a benzene, right? And what's that at 7? Oh, it's a benzene, right? So I can kind of quickly figure out what this is. That's a benzene. I'm not even going to do the table. I recommend the table, but I'm going to expedite this one. If you look at that little chart of common multiple patterns, a CH and 2 CH3s, a CH and 2 CH3s is an isopropyl group. And so you can see what the product is. It's just isopropyl benzene. So yeah, that's pretty cool. Not too easy though. This is definitely not an exam level problem. Okay. All right, cool. Let's. That was problem number 6. Way too easy. Let's keep going to some more hard ones. And here's a hard one. Hardish. Kind of a little hard. It looks so simple, yet it's so difficult. Remember, you have all these in the PowerPoint. This is problem 7. C9H12. UN's 4. Let's tell you. Okay, so 4 benzene. Okay. So if you make, this is a case where the molecule is kind of so simple that it's misleading a little bit. Because if I do the table, what's my table? Delta H S. You might say, well, I got 7 or 6.8, 1 singlet, and then over at 2.1, I got 3. And I got a singlet, right? So you might, you could get confused by this, because, I mean, what is this? How do I make my little substructures? That's kind of hard here, and the reason is because we have 12 protons, right? How can I have 1 and 3 and it come out to 12? Maybe no. We talked about this at the very beginning of this lecture series. What was the explanation for, like, if I like integration? Somebody said some protons don't appear, and somebody said no n+1. Well, there are no n+1. These are isolated, so there's no splitting. But somebody got it right. You got to multiply them by 3. This is a highly symmetrical molecule. So H, this is misleading. This is not actually what this is. Remember, integration is relative, so we have to multiply all of these by 3, and then it'll all add up to 12. So What's 3 times 1? This becomes actually 3. What's 3 times 3? It becomes 9. Okay, so now it makes a little more sense that, well, now it adds up to 12, right? So we did, I mean, we took something that's relative and made it absolute. Okay, so this 6.8 is a benzene. And how many protons are on the benzene? Well, 3 protons, right? 3 protons on the benzene. That means that how many substituents are on the benzene? If there's 3 protons, that means there must be 3 substituents, right? It's a benzene with 3 things on it. A benzene with 3 things on it. What do we say? Is it monosubstituted, disubstituted, or trisubstituted? It's a benzene with 3 things on it and 3 hydrogens, so we say it's a trisubstituted benzene. It's a benzene with with 3 things on it. So what do you think is 2.1 then? 2.1, 9. 9 means maybe some methyls, right? How many methyls do we have? 9 protons means 3 methyls. So that's probably CH3, 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 right? You got 3 methyls. And then this benzene then, how do we draw it? It's a benzene with how many squigglies? 3 squigglies and 3 H's. So I'm going to put them down here because we could, we could have, here's a benzene. You could imagine, oh, squiggly, squiggly, squiggly. That's one way you could do it. But what's crazy here, and it could be like 3 methyls, right? Methyl, 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 methyl. The problem, though, is that if this is a singlet, if the aromatic signal is a singlet, it means that these are not going to be next door to each other. None of these are next door to each other, right? Because this would potentially be a doublet. That could be a doublet. That could be a triplet, right? Because there's two neighbors. So are there any other ways I can draw this where there are no neighbors? And the answer is, there we go. Because if you do this kind of tri-substituted benzene, now these H's are all separated from each other, and you'd expect a singlet, right? So this is what it's going to be. It's going to be a benzene with 3 attachments that are all connected to methyls, and they're all separated from each other. And if you do this, it's going to be a singlet, a nice clean singlet here and a nice clean singlet here because they're all symmetrical. So the final answer is trimethylbenzene, right? Trimethylbenzene. So yeah, that's a I don't know. Is this like a problem I think is kind of cool? No, I think it's kind of boring. I don't think symmetrical molecules are that interesting, but it's a nice one for us to try here, just to practice our skills a little bit, right? And this is totally consistent with the data. You're not going to see overly symmetrical molecules like this on the exams, but it's a good practice problem. That was problem 7. Okay, back to problems that I think are maybe more exciting because we have a bunch of signals we have to interpret. Problem 8. UN is, what was it? 2 times 9 is 18, add 2 is 20. 20 minus 12 is 8. 8 divided by 2 is 4. So UN4, benzene. UN4 is benzene. And we already see that signal. 5 protons at 7 point something. Yeah, it's a benzene. Okay, so, and then we have a bunch of other cool little stuff here. And that's probably an OH, the little singlet here. So let's make a table. Delta HS. Okay, I'll go left to right. 7.2, 5 protons singlet. 4.5 is a triplet. Triplet of 1H. 2.1 is a singlet of of one proton. Probably an OH. I'll just put it out there. Probably an OH. Likely it's an OH. Then we have 1.7 quintet. Quint. Sometimes called a pentet. And that's 2. Triplet at 0.9. Triplet of 3H. Okay, there's our table. Let's make our little chart. 5 protons in benzene. Is it monosubstituted, disubstituted, trisubstituted? 5 protons, so it's a mono. Benzene with 1. And then this is a, looks like a CH here. I'm going to draw, just because I'm out of space, I'm going to draw it over here. This 4.5, I'm going to draw a CH over here. Okay, and then we have the OH, and then this is a, just looking at integration, obviously a CH2. Oh, CH3. Okay, those are the pieces. Do we have any mystery functional groups? How do we know if we have any mystery functional groups? We count everything up. 6, 7, 8, 9 carbons. Okay, we got our 9 carbons. That's a good sign. We have our oxygen, and we have 12 protons, maybe? 5, 6, 7, 8, 9, 10, 11, 12. All right, so there's no mysteries. This is a non-mysterious molecule. All right, so how do we quickly snap this together? Where's the oxygen connected to? The alcohol must be connected. I don't know. What do you think? Which signal? The CH with the 4.5. Yeah, the alcohol is connected to the CH. So let's put that up there. All right. The quintet. What does quintet mean? It's next to how many neighbors? Quintet. It's 5 lines. Quintet must be next to how many protons? It must be next to 4 protons. So quintet is the number 5. But remember, the n+1 rule means it's 4 neighbors. So oh wow, I have 1, 2, 3, 4. So the CH2 must be connected in this little to the CH, and the CH3 is on the other side. So it really becomes CH2, CH3, CH2, CH3. So that quintet really helped us. And now you can see what the answer is. It's benzene connected to this thing, all right? It's cool. So I could redraw that maybe as benzene, OH. That's the final answer, right? We getting this? It's kind of cool. It's, you know, the more you do it, the easier it gets. Let's try another one. Any questions on 8? This is a relatively easy one. Okay, 9. Okay, so this one is a little scary because I give you some carbon data, but you don't really need the carbon. And generally speaking, I always give you the proton, and you can always solve this with a proton. Sometimes the carbon might clarify some questions, and in this case, it's there just to confuse you. So, but the big thing is there's some aromatic, a couple aromatic signals, and a couple carbon, like alkyl, maybe CH2s here. Let's just let's make the table. Oh, UN. How do we do chlorines? What do? We don't just ignore them. Chlorines have to be replaced with hydrogens. So we turn this into C9H12. Okay. So C9H12, 2 times 9 is 18, 19, 20. 20 minus 12 is 8. Divided by 2 is 4. 4 is a boring benzene. It's a benzene with a benzene and no other mystery functional groups, or like C double bond those. It's just a benzene. Okay, and now this is a little scary because just to make this more challenging, I did not tell you the integrations. So H, we're gonna have to figure out. On the exam, I always do give you the integrations, but this is like a real world problem where I don't necessarily tell you the integrations, but we'll figure it out anyway. So let's see. Okay, 7.5, I'll say doublet. We'll do the integrations last. 7.2 doublet. Then we have at 3.3 triplet, 2.6 triplet, 2.0 is a multiplet. It's some crazy multiplet. I don't know. We could try to analyze it, but let's just say multiplet for now. Okay, so what are the H's? How do we do that? Remember how we do that? We have 10 protons. So we got to come up with a system that adds up to 10. And conveniently, the integration is the little curve, right? Well, it looks like this distance is the same as this distance, is the same as this distance, is the same as this distance, is the same as that distance. And then it could totally be 2 to 2 to 2 to 2 to 2, and that should be 10. And that's exactly how you do that. So we just look at the area under the curve, which is the little distances under the line. So it becomes 2, 2, 2, 2, 2. All right, so that wasn't that bad. If one of these was like a larger distance, you might say, oh, it might be like 3 or something, right? Okay, now the substructures. This one's a little challenging because all the benzenes so far have been 5 protons, right? 5 protons, you say monosubstituted. Well, this looks like, 2 doublets. 2 doublets in the aromatic region, 2 doublets, because that's the 7-ish region, right? 2 doublets adds up to 4, so it's not monosubstituted. What's 6 minus 4? 6 minus 4 is 2, so is it monosubstituted or disubstituted? There's 4 protons. That must mean there's 2 things left over, and we say it's a disubstituted. I'm going to draw the line here. It's a disubstituted benzene, right? It's a disubstituted because there's 4 protons. There must be 2 things. So now let's go back to our memories of like what are the different types of disubstituted benzenes. Let's draw them up here. There's 3 of them, right? There's 3 types. There's para, ortho, and meta, right? Ortho, para, and meta. Ortho, and there's para and meta. If you remember back, we did that. We analyzed the expected splitting patterns of these. Like para, you got a pair of symmetric protons, and they'd be doublets because they're next to another pair of protons. So it's like almost like 2 doublets, like a doublet and another doublet. Here for ortho, you'd expect doublet, doublet, triplet, triplet, right? A doublet, 2 triplets, and a doublet. For para, though, it's like basically a pair of doublets, right? A pair, like a doublet and another doublet, and they're symmetrical. Ortho is 2 doublets, 2 triplets. What about meta? What's the one in the middle? The meta one, the isolated proton would maybe be a singlet, and then you got a doublet, and a triplet, right? A singlet, 2 doublets, and a triplet, right? All right. So we see this pair of doublets, and we say, are we ortho, meta, or para? Pair of doublets.
Para.
Para. This is what you'd expect if you have a para disubstituted benzene. A para disubstituted, right? So, but what if we saw 2 doublets and 2 triplets? Then we say, must be ortho. What if we saw a singlet, 2 doublets, and a triplet? We say, must be meta. Okay. But with this pair of doublets, we say, it's a para disubstituted benzene. Let's draw it nicely. There's a nice para disubstituted benzene. Now these are in the alkyl region, below 4 and under is the alkyl region, and these are just normal. It's like, well, we have a CH2, a CH2, and a CH2. So these are really easy, which is some CH2s, right? CH2, CH2, and CH2. Okay, any other things we missed? Well, we missed the 2 chlorines. So how do you draw chlorines here? I don't know. What do you think? What do? We just write chlorine and chlorine. Just Cl and Cl. Okay. All right. Are we ready to start connecting? We have a benzene that's para-disubstituted, 3 CH2s and 2 chlorines, right? How do we start snapping these? And does anything really just stand out? I mean, like 3.3, I don't know, 3.3. 3.3 is maybe that CH2 is connected to a chlorine, right? Because that's 3 to 4 is kind of our like electronegative atom connected stuff. So maybe that CH2 there is connected. You have 3 CH2s, maybe one of them is connected to the chlorine, and that's probably the case. So it's a little out of focus. I'm sorry about that. If you can follow what I'm writing, I would just copy as I'm writing this. So we have CH2Cl, right? CH2Cl, CH2, CH2. Anything else? I don't know. Maybe the 2 triplets and the multiplet kind of suggests that the multiplet must probably be between the other 2 CH2s, right? So there must be a CH2 in the middle, and then a CH2 and the Cl on the other sides. This pattern, triplet, multiplet, probably suggests CH2, CH2, CH2Cl, right? CH2, CH2, CH2Cl. Erase everything now. You should be able to see what the answer is now. We got a benzene with a chlorine. Where's this chlorine? It has to. Where's the only place this chlorine can be? It can't be there because we have a middle piece, right? It looks like we have a middle piece and 2 end pieces. The benzene's the middle piece, chlorine on one side, chloropropyl on the other side. The only way to put this together now is, and I'll draw it down here, chlorine on the benzene, CH2, 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 chlorine. And these 3 lines are probably the 3 CH2s. One of them is downfield. It's probably the one next to the chlorine. And then this is the aromatic. You have some CHs and small quaternary signals. But we didn't really need the carbon here. All right. So that's problem 9. What were the hard parts to this problem? UN was easy. Maybe figuring out it was para-disubstituted. That was maybe a little challenging. Yeah. What else? What else is challenging? I mean, it wasn't that hard of a problem. I think putting it all together, once you figured out it's para-disubstituted, we didn't even use the carbon. Okay. I'm going to skip one and we'll do one hard problem, and then we're going to jump into the Alkyne chapter, okay? This is maybe a little bit of a harder problem, and it's kind of fun. Okay, problem 11 is hard. Almost all the other problems are pretty easy. If you want help with them, come to office hours. Okay, problem 11, slightly harder. UN, what do we do with oxygen? What do we do with oxygen? We ignore it, so it's 14 minus 10 is 4. 4 divided by 2 is 2. Oh, that's weird. We haven't seen 2 yet. 2 yet. It's not a benzene, and it's not just a ketone or aldehyde or a carboxylic acid or anything like that. But 2 is a little weird. We haven't seen that. All right, so here's a case. I give you carbon at the bottom, and the carbon will help us. You can see all the numbers on the PowerPoint. We'll discuss the carbon in a second. Let's focus on the proton now. Okay, so we got our little chart, delta HS. At 4.0, looks like a quartet. Q. How many protons? 2. At 3.3, we have 3.3 is a singlet of 2 protons. 2.0 is a singlet of 3 protons. 1.0 is a singlet of 3 protons. All right. Did I screw it up? Nope. I said triplet. 1.0 is a triplet. Okay, good start. Good start. We have a little table. Okay. So, and coming up with the pieces is pretty easy. We just look at the integrations. So it's like CH2, CH2, CH3, CH3. Right? CH2, CH2, CH3, CH3. That's a good start. How many carbons is that? It's 4 carbons. We look at the molecular formula. Uh-oh, C6. We have the 10 protons, but we're missing, it looks like, 2 carbons and 3 oxygens. 2 carbons and 3 oxygens. That's not just one mystery functional group. That must be 2 mystery functional groups, right? 2 mystery functional groups. Here, the carbon NMR helps us a bit. I'm going to write the numbers. One's 167, the other is 200. This is, again, a little beyond exam difficulty. So I'm going to guide us through this kind of quickly. Does anybody remember what's really, really, really downfield on the carbon? There's 2 functional groups always in the 200 to 220 range. 200 to 220. Ketones and aldehydes, right? Ketones and aldehydes are at 200 to 220. But remember, if we had an aldehyde, you'd see it in the proton, because an aldehyde has a proton at 9. So it's not, this can't be an aldehyde. It has to be a ketone, all right? So that here the carbon tells us we have a ketone. And what comes around the 170-ish region? Well, it's everything else, esters, carboxylic acids, and things like that. So this is carbon and an oxygen. So we're still missing, if we add this up, it's 4, 5, and the oxygen. We're still missing a carbon and 2 oxygens. A carbon and 2 oxygens. Must be an ester. It has to be an ester. It can't be a carboxylic acid because that would also show up in the proton. So it looks like we have to have a ester. Okay, cool. So now we have the pieces, and we can start snapping together. If you get the wrong pieces and you start snapping them together, you will always get the wrong answer, right? So getting the pieces is really the first step. Okay. So does anything stand out? I don't know. There's an oxygen. Does anything maybe connect to that oxygen? 4. I mean, 4 probably means that 4 probably means that this CH2 is connected to oxygen, right? Right. 4.0. So that oxygen is connected to CH2, which is also a quartet, meaning it must be connected to a what? Quartet must be connected to maybe a CH3, and which CH3 is it? Is it the singlet one or the triplet one? Well, remember, a quartet triplet is a signature for an ethyl group. So if CH2, top CH2 is connected to the oxygen and it's a quartet, it has to be connected. It can't be connected to a singlet because a singlet there's no neighbors, right? A singlet, whoops, sorry, I screwed up. Did I screw something up? 2.0, no, it's cool. Everything's cool. Okay, the point here is that 4.0, CH2 has to be connected to an oxygen, right? And since it's a quartet, it must be talking to something like that triplet, because quartet triplet is an ethyl group. So it's like this CH2 and this CH3 are basically an ethyl group off the oxygen. So putting that together, we have an ethyl ester. Ethyl ester. Erase the top CH2 and the bottom CH3. Okay. Any other deductions we can make? So we kind of used up the CH3, the bottom CH3 and the top CH2. Maybe that this CH2 is a singlet. It's at 3.3. I don't know. What does a singlet mean about that CH2? It's not next to any other protons, right? A singlet is isolated. So where could it maybe be that would isolate it? Oh yeah, we got rid of the ester too. I'm sorry. See, it's getting simpler. The more you can use your eraser to erase stuff, the simpler this gets. It looks like this is a isolated CH2. So where's it going to be? Where's it going to be? Maybe it's going to be between the ketone and the ester. So the singlet at 3.3, it's got to be stuck between stuff and no neighbors, right? So it's going to be CH2 basically next to the ketone. And what's the final answer now? Well, that's this other CH3, the other CH3, it doesn't have any neighbors either. The only place it can go is right there, and that's the final answer. So this is kind of a tough problem. I would say beyond exam level, mostly because you have two functional groups. Usually that's going to be, until we're a little further along, the likelihood of seeing two functional groups is pretty low, like this. And so also we kind of needed the carbon NMR to help us, like, 200 ketone, 167 ester. So, but it was a kind of a fun problem. This is definitely the hardest problem in all these lectures. I'm going to stop and move to the alkyne chapter just because we can't keep going with these. I would recommend that you try all the rest of the problems. I will give you answers to them, and you can always email me your answers and say, hey, is this the answer to number 12 or 10 or whatever? Okay, there's a couple more problems. You should be able to do them, and if you want help with them, office hours. But I'm going to start the alkyne chapter. All right, any other questions? It's pretty fun, huh? I don't know. It's definitely different than organic 1. So now we're going back to something closer to organic 1, which is the alkyne chapter. Okay, so okay, you see the alkyne chapter? All right, so first thing we got to do is basic principles of alkynes, like nomenclature, physical properties, and stuff like that. Chat, who's in the chat? So yes, we have a little bit of PowerPoint, and then we actually have a lot of reactions that will be kind of webcam on a piece of paper. All right. Okay, so chapter 13, alkynes. When you think about naming of alkynes, you might think of like ethane, propane, butane, and in order for the to formulate the name of an alkyne, the last letters go from A and E to Y and E. So this might be 2 carbons. You might think ethane, but it's ethyne, right? Ethyne. It's also called acetylene. This is used as a welding gas in welding. What do you think this is called? 4 carbons. 1, 2, 3, 4. 4 carbons. Maybe something-ine butane. And how do we specify where the butane begins? Maybe it's carbon 1. You know, the numbering either direction will give you the name. It's 2-butane, right? Here you can number left to right or right to left, and it's 2-butane. Usually you number from the side closest to the alkyne, but here it doesn't matter. Okay, now in this case, do we number left to right or right to left? It's like 3 carbons, so it's gonna be propyne, right? But we're gonna say it's, and then the chlorine is gonna be in 1, 2, 3. It's gonna be 3-chloropropyne, 3-chloropropyne. Okay. We can't number the other way. We can't say 1-chloropropyne because we're numbering at the end closest to the chlorine. Sorry, the alkyne. So it's 3-chloropropyne. What about this one? Are we going to number? Somebody said we name closest to the substituent, and that's wrong. We name closest. We number on the end closest to the alkyne. It's a triple bond, yeah. So in this case, do we number left to right or right to left? It'll be left to right because that's the end closest to the alkyne. So it's going to be, think about the name. It's going to be 1, 2, 3, 4, 5, 6. So it's going to be something hexyne, right? Something hexyne. And where's the alkyne? It's on 2. So it's something 2-hexyne. Something 2-hexyne, right? But on carbon 4, 1, 2, 3, 4, we have a bromine and an ethyl group. So it's going to be, and remember we alphabetized those. So it's going to be 4-bromo, 4-ethyl, 2-hexyne. 4-bromo, 4-ethyl, 2-hexyne. Okay. Now, if you go back to the chapter 12, the alcohol chapter, you might remember that alcohols do have precedence. So if you have an alcohol, the numbering is on the alcohol side, and the naming is kind of silly. If I ever give you one of these ones, it'll be like, here's the name, draw the structure. So that's an easy kind of exam problem. You'll see what it's like on the sample exam when we get there. But yeah, like in this case, the formula is we do a number from right to left now. It's 1, 2, 3, 4, 5. It's 5 carbons, 4 pentyne, 1 ol. Okay, and the alcohol is at the end of the name too, even though the numbering starts from the alcohol. It's, you know, silly naming things. I try not to have you memorize the rules here. So it's usually going to be, I give you a name and you draw the structure. Okay, 4 pentyne, 1 ol. So that it goes 1, 2, 3, 4, 5. Okay, so in this case we also number right to left. Okay, so it's 1, 2, 3, 4, 5, 6, 7. It's 5 heptyne is, you know, ignoring the substituents. 4, or it's 5 heptyne, right? 1, 2, 3, 4, 5 heptyne, 2 ol, and then we list the substituents at the beginning of the name. Okay, so I would argue that if I give you this name, you should be able to draw the structure, right? If I give you the name and not the structure, you should be able to figure out the structure. You start with the 7 carbons, draw the alkyne on number 5, of methyl on 4, and an alcohol on 2. That's usually pretty doable. Somebody said this is confusing, and you know, this is just the naming that they created like in the 1800s, and it's just a kind of historical naming system. And you know, alcohols are a little weird because it goes backwards. Non-alcohols you always number closest to the alkyne. They can also be substituents on rings, and the way this works is so if it's like a cycloheptane, the substituents are named like bromo, 1-bromo, and then this would be called an ethynyl substituent, 3-ethynyl. So 1-bromo, 3-ethynyl. The ethynyl means 2-carbon alkyne. 1-bromo, 3-ethynyl cycloheptane. The physical properties of these things. So there's 3 bonds, right? Triple bond, 3 bonds, right? So you have a sigma bond in the middle, a sigma bond in the middle, and then 2 pi bonds, like one that's kind of going up and down, and the other's kind of going back and forth. So it's 3 bonds, right? 2 carbons with are sp hybridized. The carbons are sp hybridized, and the structure's linear also. Sp things are linear. The bond length is short versus like an alkene. Alkenes are 1.3, alkynes 1.2. Why is that? Because an alkyne has 3 bonds. You have 3 bonds that are pulling the carbons together. So that makes sense, right? 3 bonds are stronger than 2 bonds. They have a lot of energy when you burn them. Lots of energy. So if we burn acetylene, we make 311 kilocalories per mole when you combust it. And the temperature is super high. It's 2,500 degrees Celsius. And so that's why we often use acetylene as a welding gas. It's probably most commonly used in the world as a welding gas, because it creates these high temperatures. We can melt metal and fuse metal together. Now, if you remember back from chapter 12, there was this concept of heat of hydrogenation. Heat of hydrogenation. What that means is you can reduce an alkene, you can reduce an alkyne, right? And when you reduce it, you're adding H2. And so we go from this 1 butene, 4 carbon alkyne, you're adding hydrogen to it. So you're adding two hydrogen molecules, and you get butane, right? Butane, butane. And you can also do it for another alkyne where it's in the middle. One's at the end, one's in the middle, right? And it also makes butane. They both make the same molecule. But one of them produces more energy, almost 70 kilocalories per mole, than the other, 65. So does that tell you something about the stability? Like, one's producing more energy when you hydrogenate it, and the other is producing less energy when you're hydrogenating. So which of these is more or less stable, top or bottom? The one that's less stable is maybe the one that produces more energy. If you're hydrogenating it, you're getting the same molecules. If I hydrogenate the top one and I make more energy, that probably suggests maybe the top one is less stable. That's exactly the case. Which is more stable? The more stable one's the internal one, the less stable one's the terminal one, the one where it's at the end. And this is exactly the same as alkenes. If you remember alkenes, we did the same thing. A terminal alkene, or an alkene with a bunch of stuff on it, is stable. An alkene kind of at the end, a terminal alkene with nothing on it is less stable. So it's the same exact thing as we learned in the alkene chapter. So an internal alkyne is more stable. A terminal alkyne is less stable and produces more energy when you hydrogenate it. This is actually the same reasoning if you look back in the alkene chapter, and we're not going to really go into this more detail, but it's a concept called hyperconjugation, and that basically the things on the alkyne or the things on an alkene stabilize it. Okay, so this is a more stable alkyne, this is a less stable alkyne. The other thing is that sp are slightly electron withdrawing. So both of these alkyne carbons are sp. They're pulling electrons, and you're giving them electrons to tug on from the CH3s, and that's what stabilizes this. The terminal one, there's only one group on it, and that's not as stabilizing. So the more groups, the more stabilization. That's another way to think about it. And that's what sp are electron withdrawing. Okay, so we'll finish on this really critical topic. If we consider alkane versus alkene versus alkyne, alkynes are kind of acidic, right? The pKa, remember that concept? So pKa, is this acidic compared to these? Yeah, it's like a gazillion times more acidic. pKa difference, this is like 10 to the 10 times more acidic. So alkynes are actually kind of acidic, right? And why is that? Why is that? So it comes back to the electronegativity of sp. Sp, that carbon, is kind of pulling on electrons, and that's because there's a lot of S character. It's 50% S, 50% P, right? And the S kind of stabilizes a negative charge and it's electron withdrawing. So the bottom line here is we can actually use a base and pull off that proton. It's actually an acidic proton. I can pull it off and I can go attack stuff. And that's where we'll end. Terminal alkynes can be synthetically deprotonated. That's one of the coolest things about alkynes. One of the coolest things about alkynes is we can rip off the proton, strong base, rips off the proton, and then we can attack stuff, like a Grignard would attack stuff, right? So here's an example. Alkyne, a terminal alkyne, rip off the proton. This is an incredibly strong base. This is one of the strongest bases in the universe. Butyllithium, strongest base in the universe that we know of. Rips off the proton, makes butane. Butane, very happy molecule, it's a gas. Now we got basically an organolithium. What can we do with this? Think back organic one. What can you do with an organolithium? Attack stuff. Anybody remember the things we can attack? And we'll stop then. What can you attack with an organolithium, or what can you attack with a Grignard? It's the same thing. Ketones, aldehydes, epoxides, right? Ketones, aldehydes, epoxides. We can attack stuff, or just generally electrophiles, and we can attack an alkyl halide even, and we can attach stuff. That's going to be the cool thing that sets alkynes apart from maybe alkenes, and certainly alkanes, is the ability to rip off that proton and go do stuff with it. Okay, so we're done. I'll stay around if any questions. Questions about this or questions about NMR or whatever. I'm done. Hopefully, you got a good start in alkynes and the reactivity we're going to have. But this is super cool. The ability to take off that proton and go attack stuff. All right. All right. Cool. We'll have a wonderful, what is it, Thursday? Have a good weekend. We'll all be face to face before you know it. All right. I'll hang out a couple minutes.
Professor?
Yeah.
Two really quick questions. They're kind of easier questions.
Cool. Favorite kind of questions.
It was the first slide on this last that we just went through, the chapter 13.
Yeah.
So the 2 butane and then the 3 chloropropane. So
these ones?
Those two right there, yeah. The 2 on the top.
Yep.
So I just want to make sure I'm just reading this right. So that's 2 is where the alkyne starts. So that's why there's 4 protein. Yeah. 1, 2, 3, 4.
Yep.
That's
1, 2, 3, 4. Yeah.
Okay. I just want to make sure. And then with the 3, how does that work? Because I see
3 carbons, 1, 2, 3.
Mm-hmm. And
I'm going to number, remember alcohols we number on the end closest to the alcohol. It's a dumb rule. I didn't make it up. Non-alcohols you number on the end closest to the alkyne, and clearly the left side's the closest. So it's going to be 1, 2, 3, and thus 3 chloropropane. Because the numbering is 1, 2, 3.
Because of
it's like it's funny because we don't say like 3 chloro 1 propine, right?
Yeah.
Because here we had to say 2 butane. With chloro, I mean with propine, we don't specify the location because it's kind of meaningless. If I say 3 chloropropine or I say 3 chloro 1 propine, it's the same thing. Okay. So that's kind of weird, a little different than butane. You got to specify. With propine, there's only 3 carbons. So that if I said 1, it would be meaningless, and if I said like 3 chloro 2 propine, that would be wrong.
Mm-hmm.
So it's like here, if it's not required, we don't say it. Here the first thing we decide is number left to right, and we're like, okay, we have to number left to right.
On the left,
1, 2, 3, 4, 5, 6. And when I build these names, I always build it right to left. I would, if I was doing this like an exam problem or something, I would first write 2-hexyne. I'm like, well, that's a good start, right? And then I'd think, well, then what are the other substituents? Well, I have a 1, 2, 3, a 4 bromo, and also a 4 ethyl, right?
Yeah.
The other thing about that is, remember the dumb rule from Organic 1 that you have to put them in alphabetical order.
In alphabetical, yeah. And then the tert-butyl and
B and E, yeah.
Yeah.
The tert-butyl, yeah. You know, and some of those things were the naming of that stuff we're going to not really emphasize as much in Organic 2, just because there's a lot of silly rules, and I'm trying to focus on a basic understanding of nomenclature. In Organic 1, that was like a big thing. Oh, tert-butyl, you know, you go by the B, not the T. But that's kind of like expecting everybody to know that now. I don't know. This is pretty reasonable though. It's kind of a simpler type problem.
Okay, I just want to make sure that I'm reading that right. But okay, that makes sense.
Cool. Any other questions?
For me, that's it. But thank you, Professor.
Yeah. Do you guys want to see that synthesis again? It's pretty cool. I can step through it.
I would.
You want to see it? All right. I'll just step through a couple of the parts because you're going to learn all this stuff in Organic too. This first thing, I'm actually this might be beyond, probably a little beyond your level, but these things react to make this thing called an enamine. It's got like a kind of alkene and a amine. This is actually a nucleophile though, a really cool nucleophile, and then it attacks on this position, attacks this thing, kicks off a leaving group, and it builds this keto ester. It's like a ketone and an ester type thing. So it's kind of like this nitrogen lone pair swings down, the double bond attacks, kicks off the chlorine, and you get this thing. So I just built this. This this enamine I can take off with acid. So acid wipes it off, and you get a ketone back. So this is back to a ketone. This stuff is a nucleophile, and it basically the two nitrogens are nucleophiles, and they both kind of like one nitrogen attacks this ketone, the other attacks the other ketone, and you end up basically getting this crazy ring thing, a ring system. So this reagent, this one reagent, methylhydrazine, builds a ring because one nitrogen, this nitrogen attacks here, the other nitrogen attacks there, and that's because there's some kind of favorance for all that, and that builds this whole ring. And we made it. Every one of these I did NMR on. Every step of this, I was like, I verified this chemical structures with NMR, which is cool. It turns out that this actually, there's a two possible products. One where the methyl is here, and the other where the methyl is here. But I'm able to separate these, and I actually make more of this one, which is the one I want. This is the one I want, okay? And then we use a strong reducing agent, like you know about sodium borohydride, right? NaBH4 from Organic 1.
You used it in the last exam, right?
Yeah.
From last semester.
What's that?
It was from the last exam on the last
semester. Yeah.
Right?
Yeah. Sodium borohydride, NaBH4, that reduces ketones and aldehydes to alcohols. It does not touch esters, because I got an ester here, right? And lithium borohydride happens to be a stronger reducing agent, and it actually reduces an ester. So it takes that ester and knocks it down all the way to the alcohol. Really cool reagent. So I go from the ester, I convert the ester to an alcohol, right? Just with a strong reducing agent. And it's essentially H minus attacks, and then, you know, a couple steps, kicks off the ester. And you'll learn this mechanism in Organic too. All right, then we have an OH, and all we want to do is convert the OH to a BR. You learned a way to do that in Organic 1, remember? PBr3. PBr3 converts an OH to a BR. It turns out that PBr3 is kind of a nasty reagent. It's a little, just kind of makes a lot of acid and stuff. This Bach thing is acid sensitive. It's a protecting group. Remember protecting groups?
Mm-hmm.
Talked about protecting groups in Organic.
We changed it into an alcohol. Right?
And so yeah, we learned about how to protect an alcohol, right?
Yeah.
Bach though is an amine protecting group. There's a structure of Bach. See it here?
do we learn that in this?
You did not. That's an organic 2. Maybe your end of organic 2, maybe advanced topic. But Bach is an abbreviation for this crazy thing up here. And Bach comes off with acid. It's an acid-sensitive protecting group. So later we'll see it comes off when I expose to acid. But there's this reaction called the Apple reaction, spelled weird. It actually is a really cool reaction that very cleanly converts an OH into a Br. Okay. Why do I want a Br? Br is a leaving group, right? OH is not a leaving group. So I need to convert the OH into a good leaving group. And then once I got a good leaving group, I use a base. A base, cesium carbonate's a base. And OH is a ether synthesis, chapter 9 of the textbook, right? We're going from a Br, alkyl bromide, with a base and a alcohol. So essentially the base takes off the proton, and then the O- attacks SN2 reaction.
It's an SN2 reaction. Okay.
What's that?
No, it's an SN2 reaction.
Yeah, total SN2. With just a funny base. Cesium is a really cool, cesium carbonate's a really cool base. It's better than like potassium carbonate and sodium carbonate for some various reasons. So this is a very commonly used base that just works really well. And DMF, from DMF, it's a SN2 solvent, right? Yeah. It's really good at SN2 reactions. Anyway, so that builds the ether. And then, so now we got this ether. We got the Bach protecting group on the nitrogen. And TFA now is a super strong acid. Trifluoroacetic acid. It's acetic acid, right, with 3 fluorines. The 3 fluorines make it like a gazillion times more acidic than acetic acid. We'll actually learn about that in this course. We'll talk about why this is such a strong acid. It's the fluorines make it most acidic. But what happens? It just kicks off the Bach group. So now we have an amine, right? And basically the last step, which I did yesterday, literally, was this mixture of stuff created an electrophile, which is essentially this chlorophenyl thing. And then the nitrogen attacked it. It made it's a little beyond this course, but it's just an electrophile. It's called an isocyanate. Anyway, all of this is an electrophile. This mixture created a functional group called an isocyanate, and then the amine attacked it, and that's it. So pretty cool. And I finally got my NMR of this like an hour ago.
Oh, and I was
like I literally just made it. I finished the synthesis last night, and the NMR was booked all day. So I was like, oh, I can't get my product. I was like freaking out. Like how can I'm not gonna be able to sleep until I get a good NMR of this, because I spent 6 weeks doing all this crazy stuff.
Is this the one you were testing last semester too?
What's that?
Is this the one that you were working on last semester also?
I think I started it maybe in December. I certainly started the process. I was probably at the first couple steps of this. But this just shows, organic synthesis. It's like, I can start with something kind of simple, do a series of chemical reactions to gradually build this. And this is an inhibitor of a protein, a chloride channel that we're interested in. Now that you've this finished, what comes after? Great question. Now that you've finished. So the story behind this molecule is a little complicated. It's called a positive control. It's like I need to test my assay, like an inhibition assay. And the reason we made this is actually because we made about 30 compounds in my lab that are not related to this, but they inhibit the same protein. And this is just a control. It's like we need to test our assay. And this IC50 is a potency of the molecule, and we have 30 other molecules that we made, and we can't test those until we make this. So that's why I had to make this. But another thing is we want to do, say I make a bunch of this amine, right? What if I make a bunch of this, then I can make a whole bunch of variations of this, where I have like 4 bromine, 4 fluorine, 3 chlorine, all these kind of variations on this benzene, right? And then we're going to test those also, because I think those might actually be more potent than this one. So this we just need as a control, but I'm like, like maybe later we can just make a bunch of variations of benzene with different things instead of chlorine, we'll put a bromine. Instead of bromine, we'll put a fluorine. Or instead of this para position, maybe we'll try the meta position, or maybe the ortho position. You know, like that's what we call medicinal chemistry. There's no logic to it, right? Like this is not something like, oh, we plan this out, right? It's not like I'm planning this out. A lot of this is blind. I have no idea how the protein fits this molecule. It's a big protein, you know, and the molecule sticks in there, and then it inhibits it. And then, of course, then this can treat cystic fibrosis, for example. There's a lot of diseases related to the protein. That's why we want to do this, because we can basically make a new drug. So no logic, but a lot of legwork. That's right. You know, but the thing is, if I make a bunch of this, which now we know how to make this, then the legwork's not that bad, because I can take this and I can easily make 10 different variations of this, right? And that's not that much legwork. This is a single reaction that I can do this in 4 hours, you know. So I would say a lot of legwork to go from here to here, but then a little legwork to make a library of analogs. So, but that's like, you know, that's organic chemistry, and it's easier once I've done all this to make a bunch of this, right? So anyway, yeah, that's like most of the projects in my lab are not a 10-step synthesis. It's like a 3-step synthesis. 3 steps we can do quickly. This was kind of fun because I got to do some new stuff. I've never done an apple reaction, for example. I had to research this and figure out, how do you do this apple reaction? It took 3 times until I got it to work. Now I can do it 1,000 times. It'll work every time. But and some of the other steps didn't work, and I had to, you know, figure it out. And so that's what I like about organic chemistry, is I'm actually learning stuff all the time. It's not like I know everything now and just get to, you know, do what I know. A lot of these things, there's little tweaks and tricks that you have to try it, fail, try it, fail, try it, fail, and then finally get it, and you're like, yeah, it works, you know. So anyway, that's organic synthesis. Imagine doing this with a 30-step synthesis. There's a lot of 30-step synthesis of stuff, and I'm blown away by that. I've never done a 30-step synthesis. This is probably the longest synthesis I've done in my life. So anyways, all right, any other questions? I gotta get out of here.
Really quick question.
Yeah.
How long do you think mechanisms get for this semester?
Yeah, good question. Like this enamine reaction, you're going to learn the enamine mechanism. This thing's called enamine, E-N-A-M-I-N-E. This is like 10 steps. It's a 10-step mechanism. Yeah, you'll do it, but it's taught in a way that it's kind of sequential. It's not like I just throw out a 10-step mechanism. It builds on another mechanism. That's like a 5-step mechanism, and that builds off a 2-step mechanism. So it's taught in a way that the 10 steps is not really that big of a deal, because there's a lot of patterns you follow. Once you get the pattern down, it's like, oh, I'm always doing the same silly pattern over and over. So maybe upwards towards 10 or 12 steps, but let's not freak out yet about that.
Okay.
Definitely, you freak out. Exam 3 has some of those kind of tough mechanisms, but a lot of the students love it. They're like, wow, there's actually a lot of rhyme and reason to it. Biochem, there's no rhyme or reason. Biochem is cool. Oh, enzymes, they do all this crazy stuff, but you won't get to learn any cool mechanisms because they're all kind of enzyme magic, right? Yeah. Here, it's going to be following a lot of patterns. When we follow a pattern, 10 steps is no big deal. So
okay, and we'll get a lot of
really fun. I promise you'll like it. Okay. As long as you take it one step at a time.
Yeah, sounds like fun though. Hopefully.
All right.
Thanks,
cool.
Professor.
Have a wonderful weekend, guys.
You too.
Bye-bye.